All right. Now, we are going to talk about the one-way independent ANOVA, and again, a lot of this is going to be review for you, but then I'm going to talk about what the F value does in ANOVA. So far, you've just learned what F does for Levine's test, but I have to explain what's going on with the ANOVAs. All right, so let's just start though with our checklist. You should be familiar with this procedure by now. We're going to look at the checklist. We're going to look at hypotheses. We're also going to look at the assumptions. Okay, so first off, the checklist. You have one factor, that means one IV, and remember, 3 or more levels. All right, so a lot of people, when I ask them, what does this word mean? They say it means you have one level. No, it doesn't. This word tells you how many independent variables are being analyzed. So a one-way looks at just one independent variable, one factor. Okay, next, different participants are tested in each level. And do you remember what that means? What do we call a factor where you have different people in each level? And I should add they've not been paired or matched. Well, let's just add that now. What do we call that factor? Between subjects. All right. So I guess a challenge for you is keeping these 4 words straight in your head. Between subjects, within subjects. Between groups, within groups. So between subjects and within subjects, you already know the definitions for. Between groups and within groups is something you're going to learn in this lecture, okay? We haven't really covered it. Also on the checklist, you are looking for a difference between means. All the t-tests, all the ANOVAs, we're trying to figure out if we have any differences among our means. All right? What are we not looking for? Say it loud. Dare you. We are not looking for the R word, right? We are not looking for this. That's going to be the last 2 chapters. All right, chapters 11 and 12 will be able to say this word freely, but not now. Okay, what about the assumptions? Well, I'm sorry, the hypotheses. We'll start with hypotheses. What about the hypotheses? HO would say that mu1 equals mu2 equals mu3. Now, if you only have 3 levels, that's where you would stop. But if you have a 4th level, then you're going to have to add equals mu4. If you have a 5th level, you have to add equals mu5. All right, so mu k just means you stop when you have reached the end of the number of levels you have. So k just refers to the number of levels in your study, in your analysis, I should say. So if you have k equals 10, that means you have 10 levels. So you're going to have to go mu equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If k equals 8, it means you have 8 levels, and you're going to stop at mu equals 8. Okay? HA is going to be written this way. We write it out in words. It's hard to do this in symbols. You have to kind of explain it in words. At least 2 of the means among all of these, at least 2 will be different from each other. Okay? All right. And down here it says, no, k refers to the total number of means. I said total number of levels, but of course that means the same thing, right? If you have 10 levels, it means you have 10 means. Now, notice that these hypotheses, all right, these are non-directional. Can we write directional hypotheses for ANOVAs? Yes, we can. We can speculate, right? We can, well, that sounds wishy-washy. Based on educated and informed predictions, we can predict, for example, the mean for group 1 will be higher than the mean for group 2, but will be the same as the mean for group 3. So we can make directional predictions. So we can have hypotheses that are non-directional and directional. However, that's not true with the tests themselves. All of the tests in the ANOVA category are one-directional. In other words, one-tailed tests. I'm going to repeat that because it is really important. So when we do ANOVAs, all the tests are going to be one-tailed, directional tests, but they can have non-directional hypotheses if you want. Okay, so one more time, the hypotheses in ANOVAs can be one-tailed, two-tailed, directional, non-directional, however you want to use those terms. Okay, so it can go either way, the hypotheses, how you write them out. But the test itself is always going to be a one-tailed test. Always. Okay, always a one-tailed test. Now, why is that? It's because if you go back, and I'm not going to do it because it would take too long, but if you go back and look at the shape of the F distributions, they really only have one tail. It's out at the positive end of the number line, but that's the only true tail that an F distribution has. So how can you say, well, I'm going to take my rejection zone and split it between two tails when you only have one tail to begin with, right? So that's why all the tests are one-tailed tests. What about the assumptions? They are identical to what they were for the independent t-test. So now, you remember what those assumptions are. Well, do you remember the mnemonic? I showed you a piece of fruit, right? Which fruit was it cut in half? It was an apple core, right? So I showed you the apple core, and hopefully you remember what's in the core, right? The DV is normally distributed in the population. Participants are randomly selected from the population, and the DV was measured on an interval or ratio scale. Now, just like the independent t-test, there's one more. So we have the core plus one more. What is that one more? Homogeneity of variance, HOV. All right? Okay, I'm going to give you an example now of what the SPSS output would look like, and I'm going to do it in the context of it's kind of a fictional study. It was a study that my students actually did one year, but there were some flaws in the design and they didn't actually find anything. However, it's a neat idea if anybody wants to try it out. So maybe we'll find something in the future. But anyways, I'm going to present it to you and just know that the data is fictitious. Okay?